All right, so we're talking about finding the moment of inertia of a thick ring, which, by the way, yes, something I think all of you should be able to do with the material that I presented in class. So how much in depth do you want me to do this? You want me to go all the way down to drawing the little box and going through the series of
No,
steps?
I can do that part. I just didn't understand why we're not like subtracting to get like the portion of the radius of the thick ring, but
All right.
we're using like all of it.
So let me first start by saying that you can't just subtract out one disk from the other. And the reason is not as clear as you might think. It's not complicated, but it might not be as clear as you think. When we talked about doing the moment of inertia, if you'll remember, the whole point was to pick a square of the object, right? And we wanted to identify every square that was on the object and then add up every square's contribution to the moment of inertia. That was how we did it. Do you recall? Well, the thing that we did at the very beginning of that was to come up with a way of relating dm to dA, right? The density of the object. So when you were doing your work, what did you come up with for the mass? Just the mass of my thick ring? Then what did you use for the area of the ring?
I didn't use area, and that was my problem.
So here's where you'd have to make a bit of a change in how we dealt or how we set this up. There's two different radii. There's the outer radius and the inner radius, right? So I would have to set up the mass to area ratio to be pi r outer squared minus pi r inner squared as the surface area of the disk. So if you just divided by pi r squared, that would be a problem because that wouldn't be the total surface area. Now, that's the start. Of course, all the other things that we did before are still true. For example, we would say that dA is going to be equal to r d theta times dr. Do you remember that? Okay. And that dm would equal sigma times dA, where this is the mass per unit area. Right? It's just a symbol for it. Well, that's this. So to assemble my integral, the moment of inertia equals the summation of r squared dm. So my square is going to be the r. I'm going to point to it by saying the beginning quarter of my square is there. That's r. And if you remember us doing this for the disk, then the next thing we did was drop in all of the information that's sitting here. We leave the r squared. We replace dm with sigma times dA. We replace sigma with m over pi r outer squared minus pi r inner squared, and replace dA with r d theta dr. Now reorder this and recognize that for every theta, we start at the inside radius and go to the outside radius. Does that make sense? We're trying to see if we can unlock the d theta and the dr so that we can evaluate them separately. Something we talked about in class for two-dimensional ones. So I say that we can. For every theta, we're going to start here. Every theta will start here and end here, right? So we can separate them out because for every theta, we go from the inner radius to the outer radius. I know this was 3 weeks ago. Sorry, it's tough, but we did the disk already. So I'm going to separate this out and have, let's collect the two r's, r cubed times m over pi r outer squared minus pi r inner squared times dr, and then a second one for d theta. And I'll set my limits. I'm going to go from r inner to r outer. And I'm going to set my other limit from 0 to 2 pi. And I am speaking really to all the people who've had calculus. This should not have been tough. If you guys haven't had calculus, this is probably a little tough. But all of this is a constant, right? That's a constant. It all comes out of the integral. So, and the ones that we've had have all been fairly straightforward calculus problems. Don't get me wrong, all of you people who have not had calculus, this part that we just did, setting up the integral, they don't have that in their calculus class either. That's something that I've had to teach you guys how to do. The actual execution of calculus starts here. Recognizing that we take out the constants, and now we deal with the part of the problem that is calculus, which is just doing this integral. This integral is not too much to do. This one's super simple because this is theta to the 0 power. This r cubed is just a polynomial. So although I still have all of this that I have to write down, this just becomes 1/4 r to the 4th evaluated from r inner to r outer. Right, polynomial rule, add 1 to the exponent, divide by the new exponent. And this one just becomes theta evaluated from 0 to 2 pi. Right, theta to the 0 power becomes theta to the 1 power divided by 1. So, again, write all this garbage down. It's just easier to write a symbol, but I don't want to make it, I want to add something that you've never seen. So this is going to be r, well, 1/4, r outer to the 4th minus 1/4, r inner to the 4th. And this is just going to be 2 pi. All right, well, there's a lot here, but I can factor out the 1/4, and I can pull the 2 pi and all that out. Just doing algebra here. And I'm doing more algebra steps than I would like to, but let's see, this will be 2 pi m over 4 times, well, I'll factor out the pi, 4 pi times r outer squared minus r inner squared, all times r outer to the 4th minus r inner to the 4th. All good still? I can reduce the pi and the pi into 2. So that just gives me 1/2 m. And then I have a fraction. R outer to the 4th minus r inner to the 4th divided by r outer squared minus r inner squared. But I have smart math kids in the room. Or at least you guys keep saying you are. This can be reduced. The top and bottom are both difference of squares. So I'm going to act on the top and use the difference of squares to write it a little differently. R outer squared minus r inner squared times r outer squared plus r inner squared, all divided by r outer squared minus r inner squared. Difference of squares. You guys remember how to use the difference of squares? You're supposed to. As long as r squared outer minus r squared inner isn't 0, and by definition it's not, because that's the picture. The outer one's always going to be bigger than the inner one. Then I can just divide. And that's what gives us 1/2 m r outer squared plus r inner squared. I know it seems like that shouldn't be the moment of inertia, but because of the way the mass is distributed, and m represents the mass of just the outer portion, no, we don't subtract a small disk from a big disk. And we kind of are. We're just subtracting out its mass portion from the mass too, which we had to do earlier, because that's really what's happened here. All right. Whee, look at all that fun times. Fun stuff right there. Leave that on the board for the 8th graders to see. Well, they don't care. Anyway, so yeah, the moment of inertia is cut in half, so the angular speed's doubled. But I said last week that it's hard to figure out what that work would be. We can figure out the work done by doing change in kinetic energy. That's the easy way to do it. But when dealing with the definition of work as, the integral f dot dx, which is our technical definition of work, we could do it this way. We know how much force we have to endure or apply for the kid to just stand there. The force is causing a centripetal acceleration, probably friction in the shoes that they're standing with on the edge, or maybe they're holding on to a railing, but one of these forces is towards the center, and that force is based on the centripetal acceleration. Well, we can write centripetal acceleration as omega squared times radius. Well, let me use a lowercase r because that value is changing. They're starting at 2 and walking towards 1. So the value of this force is changing as they walk towards the center. That would make for a pretty hard calculation for work because the force is changing as the speed is changing. So as they get close to the center, the speed is increasing and the radius is getting smaller. And we would have to find a way of expressing that work. So like it would end up being, all right, the integral of m omega squared times r dr. But then we'd have to find a way of writing omega in terms of r. Well, we could. R is right there in that equation. So we could write our equation based on this function to come up with a function of omega a in terms of r. I'm not saying that you should do this. I think this would be terribly hard when all you actually have to do is change in kinetic energy. But this would be where you would calculate the work done. It'd be the force of those kids having to walk towards the center against their own inertia. So it's mathematically plausible, and everybody who's had calculus in here, it's within your capabilities of doing. But I mean, they've never asked anything like that on the exam. But it's not just about the exam. This is how physics is done. And this is how, these rules were meant to be applied. But, all right. This is part 2 of number 6. The amount of gravitational potential energy it has is mgh here, where h is going to be replaced with 2/3 L, because that's the change in height of the center of mass. Down here, we're going to have 1/2 I omega squared, and we're looking for is it the angular speed? Yeah, the angular speed of the rod at its lowest point. So down here, it'll have some angular speed as it swipes through this lowest point. We can't use m in our function here because we derived m, and we have an expression for the center of mass of 2/3 L. So m is going to be CL squared over 2. So that's m times g times h, which is 2/3 L. And I'm going to set that equal to 1/2 times I. We have to use the moment of inertia that we found, which was CL squared over 4 times omega squared. That all pretty good? You're just solving that for omega, so I think that's okay. I don't think you need me to do that. So the other version of this problem, though, is to have it swing down by it's being held by its heavy end. So that's just a little different than what's here. Let's see if we can't just clean this up and do it that way. Not a problem. Just take all that away. And let's see. So now we're swinging from this side. This will be 1/3 L, and it'll be that is the part that's changing height. So my new gravitational potential energy has to be reset for the change in height of the center of mass from this pivot point. So that's going to be mg, where h is 1/3 L. Does that make sense? But we do have to use the parallel axis theorem to come up with an expression for I. So we don't have I about the center of mass. We have the moment of inertia about the end. So the parallel axis theorem requires that you use the moment of inertia about the center of mass. But we know where the center of mass is. It's 2/3 of the distance away from the light point. Does that make sense? You guys following what I'm suggesting? So what we have to do is find the moment of inertia of the center of mass first. Now, there's a shortcut here. I'm not going to go with shortcuts. I just want to kind of show you what we're going to do. We know that, I'm just going to do this kind of separate. Oops. So do this kind of separate. The moment of inertia about here is, was it CL to the 4th over 4? That's about this point. And our center of mass is here at 2/3 L. So this is ICM. So the parallel axis theorem looks like this. We have CL to the 4th over 4 as our moment of inertia about the end. That has to equal the moment of inertia about the center of mass plus m times how much we're shifting it, 2/3 L squared. So it was shifted from here 2/3 to the left. Does that make sense to you guys? So this is how we get the center of mass. Now we have to put in what we know about m, which is, CL squared over 2. Before you do that, consider that once you get that, we're going to need to find and shift it, right? That's what we're going to do once we get that number to get the new parallel axis. So you could do this all at once, right? You could solve this for I center of mass and plug it in here. You could. Or we could just subtract these two equations and solve for I parallel. Yeah?
So can we still use the parallel axis theorem when it's non-uniform?
Yes. So, well, we can use the parallel axis theorem to get this. That's a good question. I believe you still can. But that's a good question, and I should make sure it's true.
Is it because they gave us like this, the constant of C?
Yeah, I don't want to be that person that's like that. I like to make sure that I only spout facts, and I haven't been asked that in long enough for me to know. So I'll look it up to make sure. Or I'll just remember. I'll say when I'm sitting still, I'll go and see if I can derive it real quick just to make sure that it's true. But I'm sure it was derived from the integral, so I'm pretty confident that we're okay here. But I'm going to check anyways, just to make sure. So we'll stop work there just in case. I would tell you guys to do this the way I've kind of outlined it here, but I'll make sure. Does that make sense? I'll check. I don't want to just be the person who was this kind of indicate that there's a mass here, that these are point masses. They are held apart by a light rod length L. And it was made clear in the problem that the rod had a mass that was negligible compared to the 2 point masses. So we don't have to consider the mass of the rod as part of this problem. They start the problem by saying that a 3rd point mass is flung upwards and strikes the midpoint of the rod. It's a collision problem. And they ask about the results of the collision. That problem isn't particularly interesting because it doesn't involve any rotation. So this would just be a standard one-dimensional collision. And you can choose the nature of that collision. You can have this stick to the rod, you can have this bounce off, and they give you a velocity after the fact. That one's not particularly interesting. I think that for the most part, you guys would recognize this would have momentum mv. We would treat this as something with mass 2m, and whatever the results of the collision were would determine how the system would respond, but this object's just gonna go this way after the collision. Does that make reasonable sense? Okay. The version of the problem that's interesting is the one where they take this object and they have it hit the side here. That's the one that's interesting. After this collision, the system has both a linear momentum and an angular momentum. And that's the one I want to talk about today. So to make this problem, I don't want to say more interesting or less interesting, I want you to consider two different variants of this problem, because one of them is much harder than the other one if you're not careful. And look, one version of this is the object bounces off. That's actually the easier version. And the reason, I hope, is clear, but probably not. So we fire it away like that, and then after the collision, this thing is tumbling in space with some rotation, and its center of mass is going this direction, and this ball is, say, recoiling in this direction. That's one version of the problem. So let's work this version first, because if the ball sticks to this, it changes the center of mass of the system and the moment of inertia of the system. That's a harder question. So we're gonna do the problem where it doesn't stick first, and if we have time, we'll do the problem where it does stick, because both of these are reasonable questions. This has been done just 4 or 5 times in the literature. So it doesn't happen often. It's either something like this, or it's a stick on the ice and a puck hits it. And so it's the same kind of problem. They did have one with a really big disc on the ice and a guy ran and jumped on the edge. And they had another one where a guy stood on the edge of a big disc on the ice and threw stuff off of it. These are all different versions of the same problem. And they're all slight variations. They're all done more or less the same way. So let's start with this one. And I'm gonna draw 2 cases, the before case and the after case, so we can kind of work out what's happening. So the before case, everything's at rest, except for the one mass, which has a velocity v. And then we'll say in the after case, I wonder where they are now. I live in constant fear that at any moment a middle schooler can come in my door. All right. So do we see what's happening? Hits it, bounces off at half a v. There's 2 problems to do. The first problem is a conservation of momentum problem. So the only momentum in the system is mv before this collision. After this collision, because of the recoil, the little sphere moves backwards at 1/2 v. That was the recoil velocity. This whole system has mass 2m and its own velocity, we'll say v2 or something to differentiate it. Now, this is going to be the motion of the center of mass of the dumbbell after the collision. It's going to be traveling at whatever this velocity v2 is. Pretty straightforward here. When we add the 1/2 to the other side, we're going to get 3/2 mv on the other side. We can cancel out all the m's. So this gives us 3/2 v equals 2 v2. So v2 equals 3/4 v. Not terrible. Pretty straightforward. That's the motion of the center of mass. But it has a rotational rate too. It's spinning. To do this problem, we have to consider the angular momentum of this mass before the collision. And here's where I'm really trying to make sure you understand the nature of a point mass angular momentum. We have to find the appropriate point of reference, the pivot point for this system. And the pivot point is the center of mass, because that's where it's going to rotate. Now, the definition of that angular momentum is L equals R cross P. But I'll remind you that we really don't want to use R. We want to accelerate the problem until it is just in contact right here. So we want to use R perpendicular times P as the angular momentum of the point mass. So we move the problem up and recognize that we're dealing with this part right as it comes into contact. Can't do it. Just can't grab it the way I want. Right there. So saying that it's right at that instant when it strikes it. That makes our perpendicular this distance, which is half of the length of the rod. So we start out by saying the only thing with angular momentum is the point mass. After the collision, there'll be angular momentum of the barbell plus the angular momentum of the point mass as it recoils away. We have to make sure we include the fact that this recoiled and didn't stick to it. So the angular momentum of the point mass is just going to be L over 2 times mv. That's its angular momentum. We need the moment of inertia of the dumbbell plus its angular speed to get its angular momentum. Plus, in this case, the angular momentum of the point particle is still going to be L over 2 times m, but now it recoiled, so its velocity is negative. All of that's still the same, but we now need to know what is the angular momentum, what is the moment of inertia of the dumbbell. So you're seeing all these pieces have to be done. The dumbbell is not hard, it's 2 point masses. So mr squared plus mr squared. And it's from the center, so it's going to be m L over 2 squared plus m L over 2 squared. This will be the moment of inertia of the dumbbell. So that's L squared over 4, 2 of them, so the whole thing ends up being 1/2 mL squared. It's just a lot of work for this little problem. Now, I know there's only 3 minutes left. Do you realize how much more difficult the problem is if the mass sticks to it? If the mass sticks to it, it shifts the center of mass. So you have to find the center of mass because that's the actual pivot point for your original value for the angular momentum. And worse, now you have to calculate the moment of inertia based on a new center of mass. Yeah.
So we're not using V2 in this because that's linear?
Yes. Yeah, the motion of center of mass isn't about the rotation. The question was, we're not using V2 in this calculation because it's the linear velocity, and that's right, we don't have to use that. So, tough question. I'm not doing the algebra, but do you see the pieces of the algebra you would have to do? I'm going to assign something like this for you guys as kind of part of a practice test to talk about on Monday. I think you should practice. And I have a question like this, but it's a rod. And in one example, the puck bounces off the rod, and in one example, the puck sticks to the rod. It's the same question as this, but it has those kinds of dynamics to it. You should expect your